Hello, friends. Good afternoon. Good afternoon. You cannot hear me.
Good afternoon, sir.
Hello, friends. Good afternoon.
Good afternoon, sir.
Yes, let us continue. Now, let us see the ionization enthalpy of a group 2 alkali inert metals. The ionization enthalpy of a group 2 metals. Do you know group 2 metals? Which are the group 2 metals? Beryllium, yes, magnesium, calcium, strontium, and barium. Let us see the ionization enthalpy. Ionization enthalpy. Do you remember what is meant by ionization enthalpy? The definition of ionization enthalpy. It is the energy required to remove the loosely bound electron from an atom, especially from the outermost shell of an atom. That is the ionization enthalpy or ionization energy. Now we can compare the first ionization energies of group 1 and group 2. Let us take a group 1, say group 1 and group 2. Group 2, group 1 alkali metals and group 2 alkali inert metals. Let us compare the ionization enthalpies. Group 1, say lithium, here beryllium, sodium, magnesium, then potassium, here we have calcium, etc. You compare these two. You know, the ionization enthalpy depends on two factors mainly. One is atomic size. Atomic size. That is one factor. Second factor is the nature of the electron that is removed. The nature of the electron means whether the electron is a paired electron or a single electron. So nature of electron. Nature of electron. So these are the two factors. There are other factors also. Say the shielding effect of the inner orbitals, the inner electrons. All these come into play when we deal with the ionization enthalpy. Now you consider here only two factors. One is atomic size and nature of the electron. You compare the atomic size of the two groups. We know the atomic size of group 2 is smaller than that of group 1. Beryllium is smaller than lithium. Magnesium is smaller than sodium. Calcium is smaller than potassium. Okay. So that is because from left to right, the atomic size decreases. When the atomic size decreases, the ionization enthalpy increases. Ionization enthalpy increases. So the first ionization enthalpy of group 2 elements will be greater than that of the group 1 elements. Group 1 elements. First, ionization enthalpy of group 2 is greater than that of a group 1. That is because group 2 are having, the elements are having, atoms are having smaller size. Atoms in group 2 are smaller than that of group 1. Secondly, the first electron is removed from the paired electron. It's a paired electron. It's a paired electron. So the reasons are this. One, group 2 atoms are smaller. They are smaller than group 1. Smaller than group 1. When the size decreases, the electrons are held strongly. The electrons are pulled strongly towards the nucleus. And the removal of electron becomes more difficult. Or in other words, when size decreases, ionization enthalpy increases. So that is one factor here. Second, in group 1, there is a NS1 configuration. But in group 2, there is a NS2 configuration, outermost level. The S2 electrons, these are paired electrons. Paired electrons. So from the paired electrons, we have to remove one electron. And that requires more energy, higher energy. So due to these two factors, one, group 2 atoms are smaller than the corresponding group 1 atoms. And the first electron from the group 2 elements is to be removed from the paired S2 level. Paired S2, S2. S2 is paired. We know the maximum capacity of S level, that is equal to 2. And it has got extra stability. S2 has extra stability. So the first electron is to be removed from extra stable S2 configuration, S2 electrons. So the first ionization enthalpy of group 2 elements will be higher than that of the corresponding group 1 elements. So that's about the ionization enthalpy. Ionization enthalpy of the group 2 elements will be higher than that of the group 1 elements due to the smaller size of group 2 atoms and the more stable paired nature, of the S2 electrons. Okay. Now I come to the next point, hydration enthalpy. Hydration enthalpy. Hydration enthalpy. We are seeing the hydration enthalpy a number of times. We are seeing it. What is hydration enthalpy? Suppose we have an ion, say N plus ion, a positive ion or a negative ion also. Here you consider the positive ion because we are dealing with the group 2 metals. Group 2 metals. They can form, say, Be plus 2, beryllium, then below that magnesium. Magnesium plus 2, calcium plus 2, strontium plus 2, then barium plus 2. Radium is radioactive, so it is left. So all these are forming cations, positive ions. Now, the ion is covered by water molecules. So covered by water molecules. And the process is called, what is it known as? Covering of an ion or a particle by water molecules. That is known as, you don't remember? It is known as hydration. Hydration. It's called a hydration. In general, solvation. Covering by solvent molecules. That's called solvation. Here, covering by water molecules. It's called a hydration. During hydration, a definite amount of energy is released, and that's called hydration enthalpy or hydration energy. Now you come to the variation of the hydration enthalpy of group 2 ions. Hydration enthalpy depends on the size of the ions. Size of the ions. Smaller the size, more will be hydration. Higher the hydration. Smaller, smaller the ion. Smaller the size of the ion. Smaller the ion, say higher is the hydration. Higher is a hydration. There is more hydration. If there is more hydration, there will be higher hydration enthalpy also. Now you come to beryllium plus 2, magnesium plus 2, calcium plus 2, strontium plus 2, barium plus 2. Compare the size. You know, down the group, top to bottom, the ionic size increases. So at the topmost, there will be the smallest ion. Here the smallest ion is beryllium plus 2 ion. Smallest ion is a beryllium plus 2 ion. And it is more hydrated. Smaller, say, smaller the ion, more is the hydration. Here beryllium is the smallest ion in this group. And so it is having the highest amount of hydration. And so beryllium has the highest hydration enthalpy. Greater than. Next comes Mg plus 2, greater than Ca plus 2, greater than Sr plus 2, greater than Ba plus 2. So the hydration enthalpy increases in this order. Beryllium plus 2 greater than Mg plus 2 greater than Ca plus 2 greater than Sr plus 2 greater than Ba plus 2. This is because the atomic size, sorry, here, the ionic size, ionic size changes as beryllium plus 2 less than, Mg plus 2 less than, Ca plus 2 less than, Cr plus 2 less than, barium plus 2. So barium plus 2 is the largest ion and it is having the smallest hydration enthalpy. While beryllium plus 2 is the smallest ion and so it is having the highest hydration enthalpy. So hydration enthalpy varies as, increases as Ba plus 2 hydration enthalpy of Ba plus 2 greater than Mg plus 2 greater than Ca plus 2 greater than Cr plus 2 greater than Ba plus 2. So that is depending on the size of the ions. As it is mentioned, smaller the ion, higher is the hydration. Higher is the hydration enthalpy also. Here Be plus 2 is the smallest ion and so it is having the highest hydration enthalpy. So hydration enthalpy varies as Be plus 2 greater than Mg plus 2 greater than Ca plus 2 greater than Sr plus 2 greater than Ba plus 2 barium plus 2 ion. So that is depending on the size of the ion. Okay. Next one is the flame color. The seventh point is production of a flame color. Flame color. We had seen flame color last day. Say the given compound is made into a paste with a concentrated hydrochloric acid. And the paste is shown to the Bunsen flame, Bunsen burner flame. Then characteristic colors will be imparted to the flame. Definite colors will be, not all, definite colors will be produced by certain salts, metallic salts, and that's called the flame color. Here, group 2 metals, they also produce characteristic flame color. We know the metals are, say, beryllium, magnesium, then calcium, strontium, and barium. Radium is left, radioactive. Among these, calcium, strontium, and barium, they give flame colors, characteristic flame colors. Calcium gives brick red color, red, brick red, brick, the country bricks, the red colored country bricks, not the cement bricks, not the cement bricks. You know, the red colored clay bricks, eh? That is the color, brick red color, calcium. Strontium, that is crimson, crimson. We had seen crimson red color, that's for lithium, lithium. Here, strontium also gives a crimson red color, bright red color. Then barium, it gives apple green, apple, green color, or grassy green color, grassy green color. Say pale green color. So only calcium, strontium, and barium, they produce characteristic flame colors. From the flame color, we can identify the metal. Say next year, you will be given calcium salts. You will be given strontium salts. You will be given barium salts. And you have to identify the metals present in the given salt. The metallic ion present in the given salt. One of the confirmation tests, that is the flame color. From the flame color, we can say whether it is calcium, strontium, or barium. It's a very positive test to identify and confirm the metals. Okay. Now you come to beryllium and magnesium. Beryllium and magnesium, they do not produce flame color, no flame color. They do not produce any flame color. Why is it so? Do you know the mechanism of the production of the flame color? Remember what happens when the salt is shown to the flame? What happens? Do you remember? Yes, the electrons absorb energy from the flame. The electrons get excited. The excited electron then falls down to the ground state. Then a definite quantum of energy is emitted, released, corresponding to the wavelength or frequency of the quantum of energy emitted, released, a color is produced. So there should be excitation of electron by absorbing energy from the flame. But here, beryllium and magnesium, these two are very small. They are very small. So due to the small size of beryllium and magnesium, the outermost electrons are not easily excited by absorbing energy from the flame. There is no excitation. There is no excitation of electron by absorbing energy from the flame. That's why the flame color is not produced. Say beryllium and magnesium are smaller atoms and the electrons are held strongly. The outermost electrons are held strongly so that the outermost electrons cannot be easily excited by absorbing energy from the flame. So there is no excitation of electron. There is no falling down of the electron from the excited state to the ground state. So there is no production of the flame color. So beryllium and magnesium do not produce any flame color. While calcium, strontium, and barium, they give characteristic flame colors. That is due to the excitation of the outermost electron by absorbing energy from the flame and falling down of the excited electron to the ground state, emitting a definite frequency or wavelength corresponding to the frequency or wavelength of the quantum color is produced. A definite color is produced. Because for each color, for a definite color, there will be a definite wavelength or frequency. H nu, quantum epsilon or E is equal to H nu. So the color depends on the energy. The energy depends on the frequency. Okay. So calcium, strontium, and barium, they produce characteristic flame colors. So from the flame color, we can identify the metals. Okay, identify the metals. Now come to the next point. That is point number 8. That is action with air. That is burning in air. So point number 8, burning in air, burning, burning in air. You have studied burning of magnesium in air. You have studied in the 10th standard. Magnesium. Magnesium burns in air, producing a dazzling, bright, very bright. We cannot even look at the flame. It's so bright. That is dazzling white flame, forming a white powder. You have studied that it is magnesium oxide. Here, remember, the 10th you have studied magnesium oxide only. But it's not only magnesium oxide, there will be magnesium nitride also. So there will be dazzling white flame, magnesium, magnesium, magnesium burns, in air with a dazzling white flame with the formation of a mixture of magnesium oxide and magnesium nitride. Nitrogen is an inert gas. It is somewhat inert, but due to the vigor of magnesium, the vigor of the reaction, magnesium, it can combine with the nitrogen, even nitrogen, with the formation of a magnesium nitride. Say magnesium plus oxygen giving magnesium oxide. This you have already studied. There is one more reaction, and it is magnesium plus nitrogen giving magnesium nitride. Mg3 N2, that is magnesium nitride, oxide, nitride, magnesium nitride. Okay. How to balance this? You take Mg plus O2 giving MgO, and on the left hand side there is O2, So you can write 2 MgO. Now magnesium becomes 2 on the right hand side. So 2 MgO. And to balance the other reaction, you can try with say magnesium or nitrogen. Magnesium or nitrogen. Hit and trial method. Hit and trial method. You'll get a 4 Mg and a 3 N2. 3 N2. And this will be 2. That's wrong. That's wrong. That's wrong. Let us try. Let us try. Okay. Let us try to balance it. Balance the equation. How to balance the equation? This is also must be given. That is to be removed. Okay. You try. You try yourself. You try it yourself. Let us see whether we can balance it or not. You can use a hit and trial method. Hit and a trial method. You try? Hit and a trial method.
Sir, 6
Oh,
mg
oh,
plus 2 and 2
2 into, will
gives
it be balanced? You, Mg3, N2. You try with the magnesium. Just try with magnesium. Magnesium. Mg3N2, magnesium nitride. Mg3N2, Mg3N2, Mg3, 3Mg, 3Mg. So simple. So you make a correction in the notes sent to you. Make a correction in the notes sent to you. Page number 8. Page number 8. Point number 8. Page number 8. Point number 8. Reaction is given. Okay. Mg3N2. There it is wrongly given. Mg2N3 is given. It is not correct. It is a Mg3N2. Mg3N2. Make the correction. Page number 8. Point number 8. So 3 Mg plus N2 giving Mg3N2, magnesium nitride. Okay, that is done. Now come to the solutions of alkaline earth metals in ammonia. Alkaline earth metals, alkaline earth metals in ammonia. Alkaline earth metals in ammonia. Okay, do you remember alkali metals? Alkali metals. Do you remember? Alkali metals dissolve. They dissolve in liquid ammonia, forming, give the color of the solution. Deep
deep
blue,
blue
deep blue solution.
solution.
Here we get, say, a dark blue or a blue-black solution, blue-black solution. So the ninth point, that is the solution, solution of the metals, alkaline earth metals in liquid ammonia. Solutions in liquid ammonia, liquid ammonia. So alkaline earth metals dissolve in liquid ammonia, forming a blue-black solution. Blue-black. There will be blue-black solution. Blue-black solution.
ബസ്സിന്റെ അവിടെ പാമ്പ് കേട്ടോ, ബസ്സിന്റെ അവിടെ പാമ്പ്.
Where is that? Okay, it is gone. You got it? Okay, so blue-black solution is formed. Blue-black solution. And you know how is it produced? How the blue-black color is produced? The thing is this. There is the metal, and this reacts with the ammonia. What happens? First of all, there is ionization of the metal atom, forming M plus 2 ion, M plus 2 ion, plus electron. Now, say this M plus 2 ions, Ca plus 2, Mg plus 2, etc. These are covered by ammonia. And such ions are called, forgotten, ammoniated ions. Ammoniated ions. Here also the electrons are covered by ammonia, and these are called ammoniated electrons. Ammoniated electrons. Due to the presence of the ammoniated electrons, the electrons can absorb energy, the electrons can get excited, and the color is produced. So the color is due to the formation of ammoniated electrons. Ammoniated electrons. As we have seen in the case of alkali metals, they are also, you could say, ammoniated electrons. Here also there will be ammoniated electrons. These ammoniated electrons are responsible for the production of the color, that is a blue-black color. Due to the presence of unpaired electron, the solution is a paramagnetic. Due to the presence of ammoniated ions and ammoniated electrons, the solution is a good conductor of electricity also. All these things we have seen in the case of alkali metals. The only difference is this. Alkali metals give us M plus ion, Na plus, Li plus, etc. Unipositive ion. But here there will be formation of a dipositive ion. Plus 2 ion is formed. That's the only difference. Let us think of some of the uses of alkaline earth metals. A large number of uses are there. I have selected only one use each. Say beryllium, that is used for making the windows of X-ray tubes. Beryllium, the window of X-ray tube used for making window of X-ray tube. Second, magnesium. There are a large number of uses for magnesium. Among these, you take the alloys of magnesium. It can be used in the flashlight, can be used in, say, signaling processes, magnesium. But you think of the alloys of magnesium, especially alloys with aluminum. Say, alloy of magnesium and aluminum. For example, magnesium. You need not study it now. Magnesium or a duralumin. All these are the alloys of magnesium. And these are light-weighted. They are very light, but very strong. And so these alloys are used. These alloys are used in the construction of aeroplane, in the construction of aircrafts. Lightweight, but very strong. So the magnesium and aluminum alloys are used in the construction of aircrafts. Then you come to calcium and the barium. Among the various uses, you just remember calcium and magnesium are used in the vacuum tubes. Vacuum tubes. Vacuum tube. In the vacuum tube, air is absorbed. Air is absorbed by calcium and barium. Vacuum is produced. Vacuum tubes. You know the use of radium. Radium is radioactive metal and it is used in the treatment of cancer. So know some of the uses of some of the uses, not all, some of the uses of these metals are given. Okay. Now let us say some of the compounds. We need not study the compounds. Need not study the compounds of these metals. But let us take some special cases. For example, you take a beryllium halides. Point number 11. Point number 11. Beryllium halide. Beryllium halide. 11. Beryllium halides. So these are of a special interest. Beryllium halides. They have special properties. Beryllium halide, for example, beryllium chloride, BeCl2, beryllium chloride. Let us see the structure of a beryllium chloride, for example. In the solid state, there is a chain structure with a chlorine bridge. Solid state. In the solid state, there is a chain structure, a chain structure with a chlorine bridge. See, beryllium, there is chloro bridge, see like this. Chlorine, there is a chloro bridge, see, like this. Say chain structure with a chlorine bridge, chloro bridge. That's in the solid state. It's a polymer compound of beryllium chloride. Now you heat this. In the vapor phase, some of the bonds are broken. And in the vapor state, beryllium chloride exists as a dimer. In the vapor state, it exists as a dimer. Beryllium chloride exists as a dimer. That is BeCl2 twice. And the structure is like this. See, beryllium, dimer, beryllium, say chlorine, say like this. There is chlorine. So there is dimer. It exists as a dimer. BeCl2 twice. BeCl2 twice. The vapor state, beryllium chloride exists as a dimer. You heat it to a temperature of about 1500 degrees Celsius. 1500 degrees Celsius. Then the bonds break again with the formation of a single linear molecules, BeCl2, linear monomer. Linear monomer. That is a Cl, BeCl, BeCl2, BeCl2. See here, it exists as a monomer. A monomer is a dimer. It exists, sorry, the monomer is a linear molecule. It's a linear molecule. But in the vapor phase, that is less than 1500 degrees Celsius, beryllium chloride exists as a dimer. Let us see the solubility of the sulfates. The solubility of the sulfates of group 2. Solubility of the sulfates. That is point number 12. Point number 12. Solubility of the sulfates. How do the sulfates vary in their solubility in water? So point number 13, solubility solubility of sulfates, sulfates, sulfates of group 2. Say beryllium sulfate BeSO4, magnesium sulfate MgSO4, calcium sulfate CaSO4, then strontium sulfate SrSO4, barium sulfate BaSO4. Can say that down the group, top to bottom, down the group, the solubility decreases. Say from top to bottom, solubility of sulfates decreases. Barium sulfate, beryllium sulfate, and magnesium sulfate are soluble in water. They are readily soluble in water. Calcium sulfate is only partially soluble, while strontium sulfate and barium sulfate, they are insoluble in water, insoluble. That means from top to bottom, the solubility decreases. So the solubility will be in the order beryllium sulfate greater than magnesium sulfate, greater than calcium sulfate, greater than strontium sulfate, greater than barium sulfate. That is the order of the solubility. Beryllium sulfate is the most soluble, while barium sulfate is the insoluble, most insoluble. It is insoluble. It will be precipitated. Let us think of the solubility of the hydroxides. So next point. Next point, we take solubility of the hydroxides, metal hydroxides, metal hydroxides. See, we can see that the solubility of the metal hydroxides increases down the group. Metal hydroxides solubility increases down the group. From top to bottom, solubility of hydroxides increases. So that is the next point, point number 13. Point number 13, solubility of the hydroxides. Hydroxides, metal hydroxides. Say from top to bottom, down the group, top to bottom, solubility of the hydroxides increases. Solubility in water, solubility of hydroxide, metal hydroxide increases down the group, increases. That means solubility of say beryllium hydroxide and magnesium hydroxide, that is the least. While solubility of barium hydroxide is the most. So we can compare the solubility as solubility of magnesium hydroxide, MgOH twice, less than calcium hydroxide, less than strontium hydroxide, SrOH twice, less than barium hydroxide, BaOH twice. That means barium hydroxide is the most soluble. Barium hydroxide is the most soluble. Magnesium hydroxide is the least soluble. Among the compounds of magnesium, magnesium hydroxide is almost the most insoluble one, the least soluble one. So it will be precipitated easily. It is precipitated easily. You have to see one more point, and that's about the axial heat on the metal nitrates. Metal nitrates. We have to see this next year. Axial heat on metal nitrates. We have to see this next year. Axial heat. So that's the last point we have to see. It is action or heat on metal 14. Action or heat on the metal nitrates. Nitrates. What happens when the metal nitrates are heated? Metal nitrates decompose with the formation of metal oxide and brown nitrogen dioxide gas. There will be formation of a brown nitrogen dioxide gas, brown nitrogen dioxide gas, and it is taken as a positive test for nitrates. Nitrates, say majority of the nitrates decompose on heating with the formation of a brown gas. So production of brown gas when the compound, the salt is heated, that is the indication of the presence of a nitrate. For example, you take a magnesium nitrate, MgNO3 twice. When heated, it decomposes, giving magnesium oxide. Then nitrogen dioxide, NO2 plus O2. And to balance, you can write it 2 here, 4NO2, and oxygen will be O2. There will be the formation of a brown nitrogen dioxide gas. So when a salt is heated, if there is formation of a brown gas, the brown gas is due to nitrogen dioxide. That shows the presence of nitrate, shows the presence of nitrate. We have to do this test next year. You will be given nitrate salts, and one of the tests to identify the nitrate salts is action on heat. So when nitrates are heated, they decompose the formation of with the production of a brown nitrogen dioxide gas. Okay, so it finishes the chapter, the alkaline earth metals, alkaline earth metals. And so now you come to the end of the S block elements. In S block, we had seen group 1 alkali metals and group 2 alkaline earth metals. Only 2 groups are there. Among the noble gases, there is a noble gas, helium. Helium 1s2, that is also belonging to the S block. Helium belongs to the S block. Strictly speaking, it belongs to the S block. Okay, so it finishes S block. We have to see 2 more chapters, 2 more small chapters. Chapters number will be 2, but the portion will be only very small. Let us see what is going to happen the next day. Okay, let me stop now. Thank you.